Hello and welcome. In this comprehensive lesson on biostatistics, we'll be diving into two of the most fundamental and widely used concepts in medical research and public health. By the end of this video, you will be able to understand and apply the principles of hypothesis testing, and you will be able to calculate and interpret correlation and regression. These tools allow us to make data-driven decisions and uncover relationships between variables. We'll cover everything from the basic theory to step-by-step calculations and real-world examples. Let's begin with our first major topic, hypothesis testing. Hypothesis testing is a statistical method used to determine if there is enough evidence in a sample of data to infer that a certain condition is true for an entire population. In other words, it's a formal procedure for investigating our ideas about the world using data. Think of it as a structured way to answer a question. For example, a researcher might ask, does a new drug lower blood pressure more than a placebo? Or, is the average weight of newborns in a certain region different from the national average? The core idea is to start with an assumption, collect data, and then see if the data contradicts that assumption. If it does, we reject our initial assumption. Every hypothesis test begins with two competing statements about a population parameter. These are called the null hypothesis and the alternative hypothesis. First, we have the null hypothesis, denoted as H0. This is the statement of no effect, no difference, or no relationship. It's the status quo, the assumption we start with. For example, it might state that a new drug has no effect on blood pressure. Second, we have the alternative hypothesis, denoted as H1 or HA. This is the statement that contradicts the null hypothesis. It's what the researcher is trying to prove. For our drug example, the alternative hypothesis would be that the new drug does have an effect on blood pressure. It's crucial to remember that we can never prove the null hypothesis is true. We can only find enough evidence to reject it in favor of the alternative, or fail to find such evidence. The next step is to set our significance level. This is a predetermined threshold that helps us decide whether to reject the null hypothesis. It's denoted by the Greek letter alpha. The significance level, alpha, represents the probability of making a specific type of error, which we'll discuss shortly. It's the maximum risk of error we are willing to accept. In biostatistics, the most common significance level is 0.05. An alpha of 0.05 means we are willing to accept a 5% chance of being wrong if we reject the null hypothesis. This is a widely accepted standard in medical research. Choosing alpha is a critical decision that must be made before analyzing the data. Now, let's talk about the errors we can make in hypothesis testing. There are two types of errors, type 1 and type 2. A type 1 error occurs when we reject the null hypothesis, but it was actually true. This is like a false positive. The probability of making a type 1 error is exactly our significance level, alpha. Let's consider a medical example. Imagine a new drug is developed to treat a disease. The null hypothesis is that the drug has no effect. A type 1 error would be concluding the drug is effective when it actually isn't. This could lead to a useless drug being prescribed, potentially causing side effects without any benefit. A type 2 error occurs when we fail to reject the null hypothesis, but it was actually false. This is like a false negative. The probability of making a type 2 error is denoted by beta. Using our drug example again, a type 2 error would be concluding the drug has no effect when it actually does. This could mean a potentially life-saving treatment is overlooked and never reaches patients. The probability of avoiding a type 2 error, which is 1 minus beta, is called the power of the test. The next step is to calculate a test statistic. A test statistic is a single number that summarizes the data and allows us to compare our sample results to what we would expect under the null hypothesis. The specific formula for the test statistic depends on the type of data and the question being asked. Today we'll focus on the z-test, which uses the z-score as its test statistic. The z-score measures how many standard deviations a data point is from the mean. In hypothesis testing, it measures how many standard errors our sample mean is from the population mean, assumed by the null hypothesis. The formula for the z-score is the sample mean, x bar, minus the population mean, mu, divided by the standard error of the mean. The standard error is the population standard deviation, sigma, divided by the square root of the sample size, nen. A large absolute value for z indicates that our sample mean is far from the hypothesized population mean, which would be evidence against the null hypothesis. Once we have our test statistic, the next step is to find the p-value. The p-value is one of the most important concepts in hypothesis testing. It's the probability of observing a test statistic as extreme as, or more extreme than, the one we calculated, assuming the null hypothesis is true. Let's break that down. The p-value answers the question, if there really is no effect, how likely is it that I would get a sample result like this just by chance? A small p-value means our observed data is very unlikely if the null hypothesis is true. This provides strong evidence against the null hypothesis. A large p-value means our data is quite likely if the null hypothesis is true, so it does not provide strong evidence against it. The p-value is a probability, so it will always be a number between 0 and 1. The final step is to make a decision. We compare our p-value to our predetermined significance level, alpha. The rule is simple. If the p-value is less than or equal to alpha, we reject the null hypothesis. This means our data provides statistically significant evidence to support the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. This means our data does not provide enough evidence to conclude that the alternative hypothesis is true. It's important to say, fail to reject, and not accept, the null hypothesis, because we can never prove it's true. After making the decision, we must interpret it in the context of the original research question. What does this statistical result mean for the medical or public health problem we are studying? Let's put this all together with a worked example, a one-sample z-test. A one-sample z-test is used to compare a sample mean to a known population mean when the population standard deviation is known. Here's our scenario. The average systolic blood pressure for adults in the U.S. is 120 millimeters of mercury, with a standard deviation of 10 millimeters of mercury. A researcher wants to know if the average blood pressure of adults in a specific city is different from the national average. They take a random sample of 100 adults from the city and find their average systolic blood pressure is 122 millimeters of mercury. So, our population mean is 120, the population standard deviation is 10, our sample size is 100, and our sample mean is 122. Let's follow our 5 steps. Step 1. State the hypotheses. The null hypothesis, H0, is that the average blood pressure in the city is the same as the national average. So, mu equals 120. The alternative hypothesis, H1, is that the average blood pressure in the city is different from the national average. So mu does not equal 120. This is a two-tailed test because we are interested in a difference in either direction. Step 2. Choose the significance level. We'll use the standard alpha of 0.05. This means we are willing to accept a 5% chance of a type 1 error. Step 3. Calculate the test statistic. We use our z-score formula. We plug in our values, 122 minus 120 divided by 10 over the square root of 100. This simplifies to 2 divided by 1, which gives us a z-score of 2. Now for the final steps. Step 4. Find the p-value. Since this is a two-tailed test, we need to find the probability of getting a z-score of 2 or higher and a z-score of -2 or lower. Using a standard z-table or calculator, the probability of z being greater than 2 is 0.0228. We multiply this by 2 to get the two-tailed p-value, which is 0.0456. Step 5. Make a decision. We compare our p-value of 0.0456 to our alpha of 0.05. Since 0.0456 is less than 0.05, we reject the null hypothesis. What does this mean? We have found statistically significant evidence to conclude that the average systolic blood pressure in this city is different from the national average of 120 millimeters of mercury. The observed difference of 2 millimeters of mercury is unlikely to have occurred by random chance. Let's quickly recap the process of hypothesis testing. First, we state our null and alternative hypotheses. Second, we choose a significance level, alpha, Third, we calculate a test statistic from our sample data. Fourth, we find the p-value associated with that test statistic. And finally, we compare the p-value to alpha to make a decision about the null hypothesis. This structured approach ensures that our conclusions are based on sound statistical reasoning. Remember, the goal is to use data to make informed decisions about populations. Now let's move on to our second major topic, correlation and regression. These are powerful tools for understanding the relationship between two quantitative variables. For example, we might want to know if there's a relationship between a person's age and their blood pressure, or between the amount of a drug administered and the patient's response. Correlation measures the strength and direction of a linear relationship between two variables. Regression goes a step further by finding an equation that describes this relationship, allowing us to predict the value of one variable from the other. Let's start with correlation. The most common measure is the Pearson correlation coefficient. The Pearson correlation coefficient, denoted by R, is a number between -1 and +1 that tells us two things: the direction and the strength of the linear relationship. A positive, R, value means that as one variable increases, the other also tends to increase. A negative, R, value means that as one variable increases, the other tends to decrease. An R, value close to 0, indicates a very weak or no linear relationship. The absolute value of pulsatile tells us the strength. An R, value close to +1 or -1, indicates a strong linear relationship. An R, value close to 0, indicates a weak linear relationship. It's important to visualize this with a scatter plot. A scatter plot shows the relationship between two variables by plotting them as points on a graph. Here you can see examples of scatter plots for different correlation coefficients. A strong positive correlation shows points clustered along an upward sloping line. A strong negative correlation shows points along a downward sloping line. And a weak or no correlation shows points scattered randomly. Now let's move on to regression. The goal of linear regression is to find the equation of the straight line that best fits the data. This line is called the regression line, and its equation is y hat equals a plus b times x. In this equation, y hat is the predicted value of the dependent variable, x is the independent variable, a is the y-intercept, and b is the slope of the line. The slope, b, is particularly important. It tells us how much we expect the dependent variable to change for every 1 unit increase in the independent variable. For example, if we are predicting blood pressure from age, a slope of 0.5 would mean that for every 1 year increase in age, we predict a 0.5 millimeters of mercury increase in blood pressure. The most common method for finding this best fit line is called the method of least squares. It minimizes the sum of the squared vertical distances from each data point to the line. Let's work through an example of linear regression. Imagine a study on the relationship between the dosage of a new drug in mg and the reduction in a patient's pain score on a scale of 0 to 10. Here is our data. We have the dosage, which is our independent variable x, and the pain reduction, which is our dependent variable y. Our goal is to find the regression equation, y hat equals a plus b times x. First, we need to calculate the slope, b. The formula for b is the sum of the products of the deviations of x and y from their respective means, divided by the sum of the squared deviations of x from its mean. After calculating the means and deviations, we find that the slope b is 0.15. This means that for every 1 milligram increase in dosage, we predict a 0.15 point increase in pain reduction. Next, we calculate the y-intercept, a. The formula is the mean of y minus b times the mean of x. Plugging in our values, we get an intercept of 0.5. So, our final regression equation is y hat equals 0.5 plus 0.15 times x. This is the line that best describes the relationship between dosage and pain reduction in our data. Once we have our regression equation, we can use it for prediction. Let's use our equation, y hat equals 0.5 plus 0.15x, to predict the pain reduction for a new patient who receives a 35 milligrams dosage. We simply plug 35 in for x. This gives us 0.5 plus 5.25, which equals 5.75. So we predict a pain reduction of 5.75 for a 35 milligrams dosage. A word of caution. We should only use the regression line to predict within the range of our original data. This is called interpolation. Predicting outside this range, or extrapolation, can be very unreliable. Let's quickly recap correlation and regression. Correlation measures the strength and direction of a linear relationship using the coefficient R. Regression finds the equation of the best fit line, y hat equals a plus b times x, which we can then use to make predictions. These two techniques are fundamental for exploring and modeling relationships between variables in biostatistics. To solidify your understanding, let's work through a practice question on hypothesis testing. A new drug is claimed to reduce the average recovery time from a certain illness. The known average recovery time is 10 days with a standard deviation of 2 days. A sample of 50 patients who took the new drug had an average recovery time of 9.5 days. At a 0.01 significance level, does the drug reduce recovery time? Take a moment to pause the video and try to solve this problem using the 5-step process we learned. Alright, let's go through the solution together. First, the hypotheses. The null hypothesis is that the drug has no effect, so the mean recovery time is still 10 days. The alternative hypothesis is that the drug reduces recovery time, so the mean is less than 10. This is a one-tailed test. Next, we calculate the z-score. Plugging in our values, we get a z-score of -1.77. The p-value for a z-score of -1.77 in a one-tailed test is 0.0384. Finally, we make our decision. Our p-value of 0.0384 is greater than our alpha of 0.01. Therefore, we fail to reject the null hypothesis. We do not have enough evidence to conclude that the new drug reduces recovery time at the 0.01 significance level. Let's try a practice question on correlation and regression. A study investigates the relationship between the number of hours a person exercises per week and their resting heart rate. The regression equation is found to be y hat equals 75 minus 2 times x. What is the predicted resting heart rate for someone who exercises 4 hours per week? And what does the slope of the line mean? Again, pause the video and try to answer these two questions. Let's look at the solution. For part A, we want to predict the heart rate for 4 hours of exercise. We plug x equals 4 into our equation. This gives us 75 minus 8, which is 67. So, the predicted resting heart rate is 67 beats per minute. For part B, we need to interpret the slope. The slope is the coefficient of x, which is -2. This means that for every additional hour of exercise per week, we predict a decrease of 2 beats per minute in resting heart rate. The negative sign indicates a negative correlation. Let's conclude by summarizing what we've learned today. We started with hypothesis testing, a formal procedure for making inferences about a population from a sample. We learned the 5 key steps: stating hypotheses, choosing a significance level, calculating a test statistic, finding a p-value, and making a decision. We also discussed the critical concepts of type 1 and type 2 errors. Then, we explored correlation and regression. Correlation, measured by R, describes the strength and direction of a linear relationship. Regression provides an equation, y hat equals a plus b times x, that allows us to predict the value of one variable from another. These two areas are the bedrock of biostatistics, enabling researchers to draw meaningful conclusions from data and contribute to medical knowledge and public health. Thank you for watching,